What is going on, everybody? In this video we're going to be talking about directional derivatives and gradients. Now, you probably just got done talking about partial derivatives in class, and partial derivatives are pretty nice, right? They're pretty easy compared to some of the other stuff that you have to do in Calc 3. And so, generally when you get to directional derivatives and gradients, well, a lot of students start to kind of get lost in class a little bit, like myself included. So in this video I really want to make that clear for you, and yeah, so let's hop into this. So real quick, I have all of the different topics that we're going to be covering in this video laid out here, and I'll have the timestamps on the left. They'll also be written in the comments, and they'll also be in the description. So wherever you want to look for timestamps, you'll have them. Also, what are these topics? So we're going to start off with a review of partial derivatives. I think that's good. We want to make sure that we're all on the same page here. And then I'll give you an introduction to what directional derivatives are. All right, and then we'll do some examples with finding directional derivatives. All right, and then after we're done with that, I'll give you an introduction to gradients, which is kind of just a little subtopic off of directional derivatives. Okay, and then we'll do some examples of finding directional derivatives and gradients. Okay, so with that being said, let's hop into our first section here, which is a review of partial derivatives. So for our example here, we want to find f sub x, which means the partial derivative with respect to x, and the partial derivative with respect to y of this function of x and y, which is 3xy squared plus natural log of y. Okay, so when we actually want to go take a partial derivative, how do we do it? Well, if we're taking a partial derivative with respect to x, well, we just treat y as constant and we take a normal derivative with respect to x. Okay, so let's go ahead and do that. Okay, just stuff that should basically be review for you. So if we want to take a partial derivative with respect to x, we will look at this first guy here, 3xy squared. If we take a derivative with respect to x, we get that the x goes away and we get 3y squared. And if we take a derivative of this piece with respect to x, well, it's not dependent on x at all, and so it's going to be 0, right? It's essentially a constant. Okay, and so that is your partial derivative with respect to x. Okay, and also you can write that as df dx with those little curly d's. Okay, and so that is your first partial derivative. Now on to your second partial derivative, the partial derivative with respect to y. This can be rewritten as f sub y of x and y. And if we are now differentiating with respect to y, well, we treat the x as a constant, and we're taking a derivative of the y. So the 2 comes down, gets multiplied out front, and so you get a 6x, and then you'll just have a y to the first power there. All right, and then you have a natural log of y. And the natural log of y, when you take a derivative of that, you'll get 1 over y. Okay, and there you have it. That is your second partial derivative. Okay, so that was pretty nice, right? But now let's think about what partial derivatives are actually telling us, right? We want to know not just how to take partial derivatives, but why we're taking partial derivatives anyway, right? What significance do they have? Okay, and so imagine if you have some surface here, which I have drawn in red. What is a partial derivative actually telling you? Well, if you take a partial derivative with respect to x, basically what you're doing by setting y as constant is you're just saying that all you're doing is moving along the x-axis, right? So you're moving in this direction. Okay, and you're just trying to see, well, if I move solely in the x direction, what happens to z, right? If that seems a little confusing, think about just in 2 dimensions, right? If we just have a regular, y-axis and an x-axis, when we take a derivative of the curve with respect to x, right? So if we take a derivative of y with respect to x, what we're seeing is, okay, well, as we move in x, right, as we move this way, what happens to y? How does y increase or decrease? Okay, and so that is the realization you need to come to with partial derivatives, right? The only difference with the surface is, well, now we can move in the x direction and we can also move in the y direction. Okay, and moving in the y direction is exactly what the partial derivative with respect to y is. We move in the y direction only, and we see, okay, well, what happens to z, right? What's that slope going to be in that direction? Okay, so we're talking about slopes in two different directions here. But you may be wondering, what if we wanted to do the slope in this direction, or this direction, or maybe that direction, whatever? If we want to take derivatives and we want to find slopes in other directions than x and y, right, because there's other directions which we can travel, we have to take a directional derivative. Okay, and that's what we're going to talk about next. So, as an introduction to directional derivatives, as I said, what if we wanted to find the slope of the surface in other directions? The answer for that was, for other slopes, we need to take directional derivatives. Now, the formula for this, the one we're going to be using, is that to find the slope in some direction described by a unit vector, right? So this unit vector will give us our direction. Okay, and remember, a unit vector has a magnitude of 1. Our directional derivative, right, du of f, that's what directional derivative of f means, is going to be or the partial derivative with respect to x times a, right, where a is that component of the unit vector. And then we have the partial derivative with respect to y of f times b, and b is that second component of the unit vector. Okay, so we got to keep that formula in mind when we go on to our examples here. So in our first example here, we want to calculate the directional derivative of the function below at the point 2, -1 in the direction of the vector v equals 2, 5. Okay, now keep in mind that the vector that we got here is not a unit vector, right? Or not necessarily a unit vector. It could be, but it doesn't have to be. Okay, the goal is going to be to find that unit vector, right? To find your x component and y component of your unit vector. Okay, because that's what we need for the formula. And so we have our function below. We have that f of x and y is x squared y cubed minus 4y. Okay, and so, well, let's take our partial derivatives, right? That's the first step, because in our formula we know that we need the partial derivatives and we need the unit vector. So we'll start with our partial derivatives. We'll take a partial derivative with respect to x, and that will be what? Well, we leave y alone, we just take a derivative with respect to x, and we get 2x y cubed. Okay, then we see that this would be a constant with respect to x, right? Because if you move x, that piece won't change, right? That's another way to think about that. Okay, and so df dx is just going to be 2x y cubed. Now, what about our partial derivative with respect to y? Or, by the way, you can, again, write this as f sub y. And if we just leave x alone this time, we are going to get 3x squared y squared minus 4. Now, we don't just want to find those partial derivatives, right? We want to find those partial derivatives at the point that was given in the problem, right? Which is, that underline might be a little hard to see right here. That's the point, okay? Because what's going on here is, we're not just taking the directional derivative at any xy point. We have a specific point that we're trying to find this derivative at, okay? So we're given a specific point in a specific direction. What's the slope? Okay, that's the idea. So let's calculate what those partial derivatives are going to be at that point. So df dx at, you could write at 2, -1. If you really want to, I mean, it looks kind of ugly, so I'm just going to get rid of that. Equals, we have a 2 times a 2 times a -1 cubed, which is going to give us -4. Okay, and next we have the partial derivative with respect to y at 2, -1, and that will give us a 3 times 2 squared times -1 squared minus 4. And that right there is going to be, well, let's see, 3 times 4 is going to be 12, 12 times a 1 is going to be 12, and then minus 4 is 8. Okay, so let's underline those two partial derivatives because those will be important for later. Okay, because those are going to be, what we plug into the formula. Cool, so next, what's the other thing that we have to do? We got to find our unit vectors, right? We got to find our unit vector, rather, just singular. Okay, so how do we find a unit vector? Okay, well, we were given a direction in the problem with a vector, and we essentially have to normalize it, right? We have to get it so that it has a magnitude of 1. Okay, how do we do that? We find the magnitude of it, okay? And if the magnitude happens to be 5, okay, cool, we divide by 5. We divide the vector by 5. And what that means is that now it has a magnitude of 1. Okay, and that's perfect. That's exactly what we want. So we need to take the magnitude of our vector, which was 2, 5, and I'll show you that right here. Okay? How do we take the magnitude of a vector? Well, we do the square root of the sum of the squares. Okay? And that will give us the square root of 4 plus 25, which is the square root of 29. All right? And how do we go about getting the unit vector now? Well, we just divide by square root of 29. So we get that the unit vector is 2 over the square root of 29, comma 5 over the square root of 29. All right? And, oh, I'm not going to circle that. I'm just going to underline it because it's going to be important. All right? And so to find our directional derivative now, okay, at our point, which is 2, -1, we need our partial derivative with respect to x, right? So our f sub x at 2, -1 times our a plus our partial derivative with respect to y at 2, -1 times b. Okay, that's what our formula says. And so, well, what's our partial derivative with respect to x? It's -4. So we get a -4 times a is 2 over the square root of 29. And then we have f sub y, which is 8. And multiplied by b, you get that. All right? And so, well, let's just distribute those through. We get -8 over the square root of 29 plus 40 over the square root of 29. And that is going to give you 32 over the square root of 29. Bam. Okay? So that is one directional derivative problem down. Remember what we did in this problem? We really just took some partial derivatives, right? We plugged in some numbers, and then we found a unit vector. And then we combined them with a formula. That was it, right? So partial derivatives, unit vector. That's it. Moving on to our next problem here, example 2. We want to find the directional derivative at 1, 2 in the direction given by the angle theta, which is pi over 6. Okay? And now we have our function below again. Okay? So this seems like pretty much the same, kind of problem, right? We're finding a directional derivative, but now we have an angle instead of like an actual direction given by a vector. So the unit vector is going to be a little bit trickier, and definitely this would have probably caught me when I was in Calc 3. But once you see it and once you've learned how to handle a theta, you'll be fine. Okay, so let's do what we did last time. Let's start by finding the partial derivatives. Okay, so let's find the. I'll write it. I'll keep my notation consistent this time, and I'll use f sub x. So we'll find f sub x first. That is going to be 3x squared minus a 3y, and that'll be it. And then for your partial with respect to y, you get a negative 3x plus 8y. All right, great. So now we just plug in our points. And we get 3 times 1 squared minus 3 times 2. And then we get right here, we get 3 minus 6, which is negative 3. Okay, and that will be important, so we underline it. Next, we want to find the partial of y at 1, 2, and that's going to be negative 3 times 1 plus 8 times 2. That gives us a negative 3 plus 16, which is going to be a 13. And we underline that. Now finally, we want to find the unit vector, right? And so moving on to that unit vector, we started out with a theta of pi over 6, right? And so our question is, how do we find a unit vector that will point in that direction? Well, the answer is the unit circle, right? That's what the unit circle is good for. Okay, and you know, you have your origin here, you have your 0 degree line there, and then let's say that this is pi over 6. Okay, well, on your unit circle, right, you have your magnitude of 1 on the unit circle because it has a radius of 1. Well, this point right here is given by cosine theta, comma sine theta. And so if we want to construct a vector, right, a unit vector, that's just going to be cosine of pi over 6, comma sine of pi over 6. Okay, so really not that bad. Okay, and so we get that cosine of pi over 6, that is cosine of 30, which is square root of 3 over 2. And sine of pi over 6, sine of 30 is 1/2. Okay, and then that is our unit vector that we're going to be plugging into this equation. All right, so now all we have left to do is plug in to our formula, right? Let's remember what our formula is. We're saying that the directional derivative, okay, at 1, 2 is equal to the partial derivative of x at 1, 2 times a plus the partial derivative with respect to y at 1, 2 times b. Okay, and if we now plug in what the partial derivative of x is, we get negative 3, and our a is rad 3 over 2. Our f sub y is 13, and our b is 1/2. Or yes, it is. Okay, good. Okay, and so now we have negative 3 times the square root of 3 over 2 plus 13 over 2. And we can combine that as 13 minus 3 rad 3 over 2. Oops, that didn't work. There we go, that's a little bit better. All right, great. So, you know, this problem actually was a little bit quicker than the last one. I know we're, getting used to doing these examples now, but really, again, it's just partial derivatives, unit vector, plug it in. So moving on to example 3, we want to find the directional derivative of the function below at the point 1, 2, 3 in the direction of the vector 2i hat minus j hat plus 2k hat. Okay, and we have our function below. Now, this function right here is not just a regular 3D function anymore. This is 4D, right? We have 3 inputs, okay? And so now what happens to our formula? Well, let's find out. Our formula is actually just going to stay mostly the same. I mean, everything is going to continue. You're still going to have the partial derivative with respect to x times a, and then you're going to have the partial derivative with respect to y times b. But now you're going to have a z component, okay? Partial derivative with respect to z times c, okay? And that is basically it. So that is going to be our new formula here. And so I'll put a rectangle around that. Okay, awesome. So let's start out again by just taking our partial derivatives. All right. When we do that, we get f sub x, our partial derivative with respect to x, and you can hopefully see here that that's going to be 2xy. Okay, and the second piece goes away. Then we can do our partial derivative with respect to y, and that ends up being x squared plus 2yz. And lastly, we can do our partial derivative with respect to z, which will just end up being y squared. Okay? So now we just evaluate at the point. The point is 1, 2, 3. So f sub x at 1, 2, 3 will be 2 times 1 times 2, and that is equal to 4. Okay, so I'll underline at the end so I don't have to keep switching colors. Okay, then we do our partial derivative with respect to y. We get 1 squared plus 2 times 3. Okay, this piece right here, that's 4 times 3 is 12. And so we get 13 here. And then we have partial with respect to z, which is y squared, that's 2 squared, and that equals 4. Okay, and there we go. That's exactly what we need. Okay, hopefully I'm not taking these partial derivatives too fast for you. That would be not fun. Anyways, let's move on to our unit vector. For our unit vector, well, what's our direction vector that we were given in the problem? Well, it was 2I hat minus j hat plus 2k hat. And I like to write these in like the angle bracket form. So we have 2, negative 1, 2. Those are our components. So we can rewrite that thing as 2, negative 1, 2. Right? Yes. And so we just find the unit vector for this in the same exact way as we would for a 2D vector. Okay, we take the magnitude. When we do this, we get the square root of the sum of the squares. 2 squared plus negative 1 squared plus 2 squared. Okay, that gives us a 4 plus 1 plus 4 is square root of 9, which is 3. All right, and so now we just have our unit vector, right? We divide by that 3, and we get our unit vector is 2 over 3, negative 1 over 3, 2 over 3. Okay, and that's also going to be important right here. Now, what do? Well, we're going to use our formula that we just came up with up here. Okay, we'll plug into this, and that'll be it. Okay, so our directional derivative of f is going to be, well, f, the partial derivative with respect to x is 4, a is 2/3, our partial derivative with respect to y is 13, and our b is negative 1/3. Our f sub z is 4, and our c is 2/3. And so putting that all together, we get 8/3 minus 13 over 3 plus 8 over 3. And that gives us, well, we have a 16 here and a minus 13, so we get 3 over 3, which is just 1. I always think it's kind of funny when you do so much work and your answer just ends up being 1. It's like, bro, I could have guessed that. like I could have just like wrote that. No, but anyways, let me move on to whatever we're gonna do next, which is Introduction to Gradients. Okay, so by the way, actually, if we've been going for, I don't know, maybe like 30 minutes so far or something like that. If you want to take like a quick 5-minute break just to relax, right, just to reset, do it now, because we only have this and then 2 more examples, and then that's it, right? So you don't want to be burnt out for this, because gradients are probably the hardest part of this whole thing to understand. Okay, so yeah, if you want to take that break, you can take it. Assuming that you've done that, let's hop back in to our introduction to gradients. So we can actually rewrite our directional derivative formula in terms of this thing called a gradient. Okay, so we'll try to see what actually a gradient is. So here is our formula. Okay, here's the formula that we've been using, and we can actually rewrite this as a dot product of 2 vectors. Okay, remember that a dot product will give you a scalar, right? And our function here, right, this thing is a scalar, right? It's not a vector. Okay, and so we can actually write it in terms of vectors as long as we take a dot product to make them to give you a scalar output, right? So what we can do is we can take a vector of partial derivatives and then have our unit vector here. Okay, and this is important, okay, because rewriting it like this, we see our unit vector and we see this thing, and this vector of partial derivatives is called the gradient of f. Okay, the gradient of f, because these partial derivatives are acting on f. Okay, and so that's what we mean when we say the gradient of f. Now the gradient pops up a bunch in like everywhere in physics, which is what my major is. We see it all the time in a bunch of different things. It's in Maxwell's equations, it's in like a lot of other things that I don't want to think about right now because I'm stressed about my homework. But anyways, yeah, this is really widely used, and we'll talk about what gradients mean for us in Calc 3. So if we take this gradient vector and we strip away the f, right? So we just take away the thing that this gradient is, or this del operator is acting on. Okay, we just get this del operator. Okay, the del operator is this symbol. Okay, it's represented by a nabla, so I guess this is actually called a nabla. That's a cool name. But basically what that is, so instead of writing it like this, we'll just say, okay, well, they're partial derivatives, they're just not acting on anything yet, so we're just kind of taking away the f that would be right here. Okay, and that's really what this del operator is. Okay, so before we actually get into what this gradient is like good for and like what it means and all that stuff, I want to make sure that we understand what an operator actually is, because when I got to this point, I'm going to be real with you, like I was confused on what was meant by, oh, this del operator. Like I kind of got a little like nervous hearing that term. So let's just make sure we're all on the same page here. So an operator is just something that like tells you to do something, right? It's something that tells you to operate. For instance, a plus sign tells you to add 2 things. A d over dx tells you to take a derivative, right? This thing right here is called the derivative operator. Okay, and a del operator, right, that tells you to multiply by a vector of partial derivatives, right? So if you are taking the gradient of f, right, if you're finding the gradient of f, right, what you're doing is you're multiplying a del operator by f. Okay, and when you do that, you indeed get this thing of partial derivatives acting on f. Okay, so that's the idea. That's the idea of what is meant when we say an operator. But we actually need to answer this question, right? Why do we care about this whole gradient thing? What's it good for? Well, for our uses, the gradient of f will give us a vector that points in the direction of the steepest slope at any point. Okay, I want to make sure that you're not zoned out right now. Okay, so if you're zoned out, I got you. Okay, this is really important. Okay, let me read it again. For our uses, the gradient of f will give us a vector. Okay, so the gradient gives us a vector that points in the direction. Okay, so this vector points in the direction of the steepest slope. Okay, at any point on this graph, it's going to point in the direction of steepest slope. So an illustration of this, imagine this thing is a extremely well-drawn mountain. Okay, we just get a bunch of these little vectors in here that point like the steepest way, up the mountain, right? It's kind of like the path of most resistance in a way, but not really. It's kind of just saying, okay, at this point, where's the steepest place to go? Okay, and if you were to follow, you were start from the bottom here, and you were to follow the gradients all the way up the mountain, you would get the steepest path. Okay, and so it's kind of interesting how this whole thing works. Okay, but yeah, the gradient of f is all these little arrows that you're seeing here. Okay, it's just essentially a field of vectors, right? It's a vector field that's, all these vectors are pointing in the direction of steepest slope. Okay, and a good way to also think about this, it's the maximum directional derivative for every point. If you understand the idea of a directional derivative from earlier, you hopefully can see how this is a maximum. Okay, if you don't understand the idea of a directional derivative from earlier, I would go review that quick. So let's actually prove this, right? Using the fact that duf equals the gradient of f dot the unit vector, and that the del operator is a vector where its components are ddx, ddy, showed that the maximum directional derivative is in the same direction and has the same magnitude as the gradient vector. Okay, so we want to see this similarity between the maximum directional derivative and the gradient vector. Okay, they basically need to be the same. Okay, and if you know your properties of the dot product, this actually isn't that bad. Okay, because we know that this is true. And, well, what do we also know about a dot product? Well, if we take the dot of two things, that's the same thing as doing the magnitude of the two vectors multiplied together times cosine theta, where theta is the angle between those two vectors, right? And, well, the magnitude of the unit vector is 1, right? And so that goes away. And so we are left with the gradient of f, the magnitude of the gradient of f, times cosine theta. Okay? Now, remember what we're trying to see here. We're trying to find the maximum directional derivative. Okay? So what value of theta would give us a maximum directional derivative? Well, if theta was, well, if cosine of theta was 1, that would be a maximum, right? Because cosine of theta ranges in between -1 and 1. Okay, and so 1 is the biggest value we can get. So what value of theta would do that? Well, if theta was equal to 0, that would give a maximum. Okay, cool. Now, we actually have just shown that the maximum directional derivative is the same thing as the gradient vector. But let's see how. First, we wanted to show that the maximum directional derivative is in the same direction as the gradient vector. Okay? Well, let's see. We see that we have our directional derivative here, okay? And we know that that directional derivative is being taken in the direction of the unit vector, right? That's the whole idea, right? Instead of just taking your derivative along the x-axis or along the y-axis, well, now you are taking it in some other direction. You're trying to find the slope in some other direction. And that direction is the direction of the unit vector that's given in the problem. Okay, and we showed that unit vector, right? The angle between that unit vector and the gradient vector is going to be 0, which means that they point in the same exact direction. So we already see that they do point in the same direction. What about, do they have the same magnitude? Well, if cosine theta gives 1, right, that goes away, and really this is just equal to the magnitude of the gradient of f at a max. And so yeah, this ends up equaling this, right? So the maximum directional derivative is equal to the magnitude of the gradient vector. And so we've shown both things, that the gradient is always pointing in the direction of the steepest slope. Okay, so kind of interesting. So let's do some practice with gradients, okay? Because that's cool and all, we're learning about gradients, but we actually have to apply what we know, right? We have to be able to solve problems and do well on tests, hopefully, and bring like decent grades back to our parents and stuff, kind of. And so we want to find the gradient of f and the directional derivative of f at 1, 3, 0 in the direction 1, 2, -1. Okay, and we have our function below. So first, we know that the directional derivative is equal to the gradient of f dot u. And so if we find the gradient of f, right, we can actually just find the directional derivative pretty easily from there. So we can do this in a process, right? Well, first we'll find the gradient vector, and then we'll use this formula to find the directional derivative. Okay, so first we'll find this guy. Okay, so we need the partial derivative with respect to x, the partial derivative with respect to y, and since this is we have 3 inputs here, okay, we're going to need a third partial derivative. Okay, and so, well, let's see what our partial derivatives are going to be. We have, and we can rewrite this as, instead of writing it in the curly d form, we can just use f sub x, f sub y, and f sub z. The reason why I like to do that is because it looks a little nicer when you want to actually show that you're plugging in a point. Anyways, f sub x is going to be, well, the x goes away and you're just left with sine of yz. Then we have f sub y. This is a little bit trickier. The x is going to stay there because it's treated as a constant out front. The sine changes to a cosine, but we have to multiply by the derivative of the inside, right? And if we're treating y as the independent variable, then z is going to be the constant inside that gets brought out here. Okay, and the same thing is going to happen for the partial derivative with respect to z, except now the y is going to come out instead. So we get xy cosine of yz. Okay, so now let's plug in our points. And our point is 1, 3, 0. If we plug that into the partial with respect to x, we get sine of 3 times 0, and we know the sine of 0 is 0. So the partial with respect to x is just going to end up being 0. Now what about the partial with respect to y? Okay, well, that's going to be x, which is 1, z, which is 0, and I don't really need to do the rest. We can already see that it's going to be 0. And then we have f sub z, which, again, we want to find that at 1, 3, 0. We have our x is 1, our y is 3, and then we have cosine of a y, which is 3, times z. And cosine of 0 is 1, so this just ends up being 3. And so, depending on what you actually wanted to find here, because I guess I didn't word this problem very, very well, because I said, just find the gradient of f, and I didn't necessarily say that you had to find the gradient of f at that point. So I guess how we would want to write the answer, right, is just as this collection of partial derivatives up here without anything plugged in yet. The reason why we actually plugged in was for the directional derivative. Okay, so sorry about that. That's kind of confusing. But, you know, this might vary between like professor to professor. They might want you to plug in for the gradient of f. Others might not. All depends. So there's your gradient of f, and that's our first answer. And then we just have to, oh wow, that didn't work out. All right, there we go. Then we just have to dot this with a unit vector. And, well, the direction is 1 to -1. And so let's find a unit vector in that direction. Okay, we take the square root of the sum of the squares. Okay, this gives us the square root of 6, I believe. Right, and then we are just going to write our unit vector as 1 over the square root of 6, 2 over the square root of 6, -1 over the square root of 6. Okay? And then to find our directional derivative at the point 130, right? Because that's the point of the problem where it said, you know, find the gradient of f, and then find the directional derivative of f at 130. Okay? So now here's where we are going to use that new gradient, right, which is just 0, 0, 3. And we dot that with the unit vector. And so the only component that's going to matter here is the z component. And so if you multiply this, you're just going to get -3 over rad 6. Right? Because you just have your x goes away, right? Your y goes away because there's a 0 here. Then you just have your 3 times a -1 over rad 6. So hopefully I didn't go too fast there. All right. I'm not having very good luck with these rectangles today. All right. Awesome. So that is our directional derivative. And so now we're just going to move on to our last problem here. And that last problem, example 5, a little bit nastier, all right, but we'll get through it. The temperature is mapped for every point, x, y, z. The function of t is given below. If you placed a particle at 1, 1, -2, which way would that particle have to travel to feel the greatest increase in temperature? What is the value of this increase? Okay, well, we are trying to find the direction of greatest increase. Okay, what is that? Well, that's the gradient of f, right? That is our direction. Okay, because remember the gradient of f is a vector, and that vector points in the direction of steepest slope. So our goal right here is going to be to find the gradient. Okay, and if we want to find the value of this increase, okay, we essentially just need to take the magnitude of the gradient, right? Because when we proved that a maximum directional derivative thing earlier, right, we were able to show that the gradient of f, when you find the magnitude of it, it equals the magnitude of the directional derivative, right? And so that's really important. So let's go ahead and start finding this gradient. We know that the gradient here, and again we have 3 inputs, so our gradient of t this time is going to be partial t partial x, partial t partial y, partial t partial z. Okay, and so we need to start taking partial derivatives, which is going to be kind of nasty because we have a large fraction here. Okay, so let's just remember something, right? We have essentially, you know, a constant over something huge. Okay, and we can kind of think of that as 1 over x in a way, right? Where x is just going to be this entire thing on the bottom. Okay, I know we already have an x down there, so maybe I'll just rewrite this as like 1 over b. Okay, so when we take a derivative of this thing, we get negative 1 over b squared, right? Hopefully you remember that derivative, right? That's a really important derivative to know, right? Just the derivative of b to the negative 1, or if this b stuff is confusing, you can think of it as the derivative of x to the negative 1. Okay? And so if you have this negative 1 over b squared, so we'll see that the derivative of this entire thing is going to be just, negative 1 over b squared, and b was this entire denominator here. Okay? And instead of a 1, we'll have an 80. Okay? And then we'll just have to multiply by the derivative of the inside. Okay? So hopefully that makes sense as to how we're actually going to be taking this derivative. Okay? So again, it's just going to be a negative 80, okay, over a 1 plus x squared plus a 2y squared plus a 3z squared. Okay, and that's going to be squared, and then we multiply by the derivative of the inside, which, if we're taking a partial with respect to x, the derivative with respect to x on the inside is 2x. And so we can rewrite this as negative 160 over 1 plus x squared plus 2y squared plus 3z squared. Oh, sorry, negative 160x. And then this is the denominator gets squared. Okay, next we're on to our partial derivative with respect to y. Now this is going to have the exact same look as before, right? So actually I'm going to copy this entire thing, right? The derivative, it's the same exact thing that I just talked about stands, right? Instead, we're just going to have a different derivative of the inside now. So that's the only thing that changes. Our derivative of the inside will now be with respect to y, right? And so we get 4y. Okay, and so now we have a negative 320y up here. Okay, so hopefully, again, that makes sense. I know it's kind of a lot right now. Okay, but let's do another copy paste here. I know you probably can't copy paste, so sorry. But if we want to now take a derivative with respect to z, well, now we have to take a derivative on the inside with respect to z. And so when we do that, we get a 6z. And so this right here is going to be a negative 480z, right? We just have a negative 80 times 6z, and that gives us negative 480z. Okay, so the partial derivatives, like, once you understand the pattern here, right, you understand how this is really similar to, 1 over x, okay, that's basically it. Okay, I know it's kind of weird to warp your head around how that entire denominator can just be written off as like an x, but, think about it as like a chain rule kind of deal. Okay, because that's exactly what it is. So that is just taking our partial derivatives here. That was the hardest part of the problem. Let's move on to kind of the easier stuff. Okay, and that easier stuff is going to be just compiling this, right? Our gradient of t is going to be, well, we can take out a negative 160 here. I mean, you can see how this is like, this is twice negative 160. This is 3 times negative 160. And so actually what I'm going to do is write this as negative 160. They all also share the same denominator. So I'll take that out too. Right? And then all you're left with on the inside of this gradient vector is going to be a x, right, right there, right, from here. You'll just, if you take out a negative 160, you're left with x. If you take a negative 160 out of negative 320y, you're left with 2y. And if you take that out of z, oops, sorry, yeah, and if you take that out of negative 480z, you get 3z. Okay, and so right there, that's your gradient vector. Okay, now we can put our point in here, right? Because if we're trying to find the direction, Okay, we're trying to find that direction at the point, because it said that in the problem. Okay, so in this case we want to find that direction at the point. In the last case it didn't really say that. It said we wanted to find the directional derivative at the point, but it didn't necessarily say that about the gradient. Now I'm sorry if that still seems a little confusing. To be honest, I'm kind of getting hung up on that myself. Like, it wouldn't, I'm sure it wouldn't be wrong if you found the gradient of f at the point anyway, because you would have had to find the regular gradient of f along the way. So don't, just get that out of your mind. I'm just confusing you, sorry. Anyways, let's move on and plug in our point, and hopefully we have, okay, yeah, our point is 1, 1, -2. I was going to say, hopefully our point is something really low, you know, in numbers, because we have some big stuff here that we're dealing with. And so when we plug in, we have a -160 over a 1 plus a x squared, which is 1 squared, 2y squared, 2, 1 squared, 3z, sorry, this should be a z, and 3 times, so -2 squared. That'll all get squared. And then we have a x, which is 1, 2y, which is 2, and then 3z, which is -6. Okay? And so then we can just simplify here. And when we do that, I'll do a little bit of the math for you, don't worry. Like, I'm not going to do this to you. You get 160 over 256. And if you also can distribute that negative through, and then you just get -1, -2, 6. Now what we have right here is the direction of the greatest increase in temperature. Okay, that's, you know, we have a vector here, and that vector is the gradient vector, so it does that. Okay, so we don't really need to actually, you know, find a unit vector at all for this problem. But we do want to find the magnitude of this, because that is going to give us the actual increase in the temperature as we move 1 unit in this greatest direction of increase, okay, or this direction of greatest increase. Okay, so let's go ahead and do that, and then we'll have solved the problem completely. Okay, but this was the solution to the first part of the problem. Okay, but in taking a, you know, since the directional derivative at 1, 1, -2 is equal to the magnitude of the gradient vector, we can just find the magnitude of this vector right now. Okay, 160 over 256 simplifies actually pretty nicely to be 5 over 8. Okay, and then we can just square root this and write -1 squared plus -2 squared plus 6 squared. That will become 5 over 8 times the square root of, get a 1 plus 4 plus 36, square root that, and then you just get 5 over 8 times the square root of 41. And right there, that is your actual temperature increase. Okay, and sorry, these should be in pink because this is our last example. And so we're in the pink section, these should be circled in pink. That needs to happen. Did I mess up anywhere else? No, okay. Good. So hopefully that stuff makes sense, okay? You really are just, you know, you're using partial derivatives, you're plugging points in, you're finding unit vectors, you're just using formulas. And so really the only hard part is just understanding what you're actually finding, right? And that's why I wanted to spend so much time on that in the beginning in our review of partial derivatives, right? I want you to understand what partial derivatives are actually finding, right? So that you understand what directional derivatives are actually finding. And if you understand what directional derivatives are actually finding, you'll understand what a gradient vector is and what a gradient vector does. Okay? So I hope this video helped. I will have a full Calculus 3 course out pretty soon, so if you want more practice problems like this, and you know you might be not doing too hot in your current Calc 3 course, and you just want a better explanation, I will have that course out very soon. You can check the description. It'll probably already be out by the time that you watch the video. So yeah, that's going to do it. I'll see you guys soon. And yeah, thanks for watching.